So hello from our side. It's Miguel and me, Fabio, as announced before. Miguel is doing the technical lead this year, and I did the project management last year. And we're going to try to give you a bit of an insight on what challenges we faced, and we really hope that especially the teams doing it for the first time this year, the driverless year, can get some inspiration and also potential problem points coming up in the near or a bit further future to kind of cover them. We're splitting the presentation in two parts. At first, I'm going to talk a bit about the project management. We're going to keep it rather short, but I still think it's crucial, especially in a first-year project where you have to set up the structure. And then we're going to switch to a technical part where Miguel is going to say most about it. So let's start with a small video to get you all interested in it. So as we said, starting with project management. In my opinion, the goal of the project management is to form a performing team, which starts at the recruiting phase, thinking about which character types and skill types fit together and how you make them work together and how you get them to talk together. Then the other part is that you make sure of good engineering practices, which is basically the question why, which you should ask a lot. Why are you investing the time in this and this? What is your main design goal? Why? How do you divide this sub-goal? Just make sure that you always can explain what you do. You should document it, and it should be clear also for the next year. That's like part of it is you can explain it later, you understand what you're doing, and the other part is like for long-term success of your association, it's gonna be easier to forward the information you have. Then the other part, which I think is really important, you keep the developers focused. Like you don't try to distract them with any operations, just try to get them the funds to create or like to actually make their implementations or their ideas happen. You try to get financials for it. You organize events where they get feedback to their concepts, or you organize events like as a sponsoring return. Like they shouldn't worry about them. They have enough of a challenge to implement their ideas. Basically, our story started with this. There were a few alumni which heard of this driverless competition. We gathered together and we met for 2 times to see kind of what the competition was all about, how much effort it was going to take. And then we said, yeah, we're hooked, we're going to do it, no matter what it takes. And that's basically the moment where we cheered. And we always said it's going to be a fun project and that should be kind of first priority. So we started off in integrating it into our association. I don't know if you know, probably not all of you know our history. So far we've always just developed one car. So at first combustion cars, but then we switched to electric, but never 2 cars at the same time. But here with driverless, where you can take an old car, it was basically the first time we said, yeah, we're going to have 2 projects. A lot of teams already do that. For us, it was a bit of a challenge. So we created a document of 6 pages at the end. And we just wanted to make sure that in times where it's going to be stressful, we have something to orient on. And at the beginning, it's a bit more calm. You can structure it down. And here's some points which we considered in that document. Probably for you, when you do it for your association, it's going to be different. So I'm just going to talk what we considered. So for us, especially in the first year, it was important to consider how is FSD going to continue. Is it even going to continue? We didn't know if is it going to be a success, this event. Is it what's going to happen? Our further partners, which is the university, the ETH in our case, sponsors, alumni, how are they going to react to it? How do we communicate the whole project? Then small points like we're going to share it with electric, so the workshop is going to be shared, tools, transport vehicles, where we go, like how do we share them, especially if both need them, who has priority? Liquidity of the association. So if we don't get sponsoring money yet, but we need some liquid assets of the association, like especially if it's getting tight, who has priority, how do we define this? Then recruiting conflict, how do we get people for both of the projects without interfering with each other? How do we set up our corporate identity? Do we have the same? Do we have the same newsletter distributor? Do we have a shared or a split social media account? It's just things which are good to think about before it's burning. That was basically the result. It's taken out of the document. That's basically, it's in German, so you see how it really was. You can look at it later. I think the presentation is also going to be shared if you're interested. Basically what we have, you have AMZ as a head structure, and then the two sub-projects which are on the same level. The two sub-projects financiate, I don't know, to the operations part. So basically they get cars, the transport cars of the association, and then they have to pay that amount back. It's basically like a company renting parts down. It looks a bit more complicated than it is at the end. It's mostly for the annual budget review. So recruiting, for us, we saw before, the guys cheering there with the beer, it was all alumni, and we realized we have like 3 people doing software, or which are interested and have time for software. And according to our analysis, there wasn't enough. So we started recruiting with this Photoshop picture back then. And the weak area was software or robotics in general, where we looked. And we put an emphasis on determination of the people and the self-initiative. So we also wanted them to make the step towards us and tell them, yeah, I'm interested, what's there to do, like give us a bit of an insight. This new challenge also brought changes to our association. Basically, the communication in the association switched, or like in the driverless project, switched from German to English. Like Miguel, he's from Spain. There were international master students joining the team, which required those changes, and there was actually no problem to do so. At the end, we were 8 software and around 80 alumni, depending on how you count them, working on the project. Work ethics, that's a few pictures taken of a previous year. I guess you all know it. I think in the electric projects, there's more but mundane tasks. I don't know, some simulations of different parts. You can do them basically in sleep. You don't need to focus a lot. It's not dangerous. You can push yourself a lot. I think in driverless, it's a lot different. You put bugs in your code. It's either going to take you a lot of time to find them again, or if the car drives, it can crash. I think it's a lot more important to keep being fresh and awake. And actually, I found no pictures of someone sleeping in the office this time, which is a big success for us, actually. That was really, really key. Team performance here, already in the electric project, you have a big multidisciplinary competition. Here, there's IT people coming in. You have 3 people, different backgrounds, different languages. Already when you start talking about coordinate systems, you need to get them on the same level, talk the same language. One thing, all right, basically this picture illustrates it for me. Miguel is going to talk a bit more at the end, but you have alumni, electrotechnicians, mechanical engineers, software people, all working on a problem we had in FSG, and we actually managed to solve it in a very short time because the team performed together. One thing I want to say here, robotics and IT people tend to be used to having robots which kind of work or are industrial products. So what we did to make them aware of how complex this prototype is actually tell them, like the sensor you want to use, you put them on a car. So you make sure how does the wiring go there? How do you power it? How do you actually mount it there? And they got support of other people which knew how to do it, but that made them a lot more aware on what's actually behind this platform we are using. The last point is budget and sponsoring. For us, we had a lot of common sponsors of the electric and the driverless team, and we decided to split the 2 projects. But it's very important to not anger someone, or like someone sees here like a new, I don't know, they somewhere see, I don't know, AMZ without their logo, and they think, yeah, we're sponsoring AMZ. So it was very important for us to communicate. We do this new project, and we put a lot of effort in not angering anyone, or like we thought the driverless project is going to pinch the whole AMZ community, or the AMZ association, but it was very important, and I think it's very important for all of the teams to know how to communicate or to think about it, how you bring it out. It has a big potential, like it's the technology of the future, or whatever you want to say, I think most people are interested in it. it's not a bad thing, for sure. Let's go over to the technical concept.
So yeah, I will introduce now the technical concept. Everything that we developed, hardware and software, was based on two main goals. We wanted to make a reliable and competitive autonomous platform. With reliable, we mean that it had to be redundant to any single mode failure. So if the LiDAR failed, if the camera failed, if any single thing fails, we want to keep running, even if the performance deteriorates, but we have to finish the race. If two things fail, then we want a fail-safe strategy, so something that doesn't blow up or something that doesn't come crazy. So we want a guarantee that everything comes to a safe stop. With competitive, we mean that we don't want like a slow robot that you can go faster by running. We wanted to, from the beginning, all our calculations were assuming that we could get close to the limit of the car, close to the limit of the tires. Oral velocity calculations were for more than 80 kilometers an hour, whatever you design, the vision system, the velocity estimation. So we, from the beginning, aimed to be high performant. Well, this is the result that we got at some point in the season. You can see the throttle command from the computer, the speed, and the GG plot of the acceleration. To do this, we use Fluella as a platform. It's a four-wheel driven electric car, full aerodynamic package, high wheel torque, and lightweight design. It was designed and built by AMZ in 2015. And the best thing we can say about Fluella is that it was very reliable and robust. Mechanical and electrical things worked. They almost always worked. And whenever they didn't, we had some alumni from 2015 that helped us solve the problem by basically just being in charge of their own part. So that was a really nice thing, that we had support, and whenever we had problems, we could be backed up by the alumni. To make Fluella being able to race autonomously, we needed to enhance their capabilities. So the first thing you need to do is substitute the driver. So you need some sensors, some actuators, and some computing. In a Formula Student driverless setup, the first thing that tells you where to go is where are the cones. So you need a perception system that we made redundant again. So we put a LiDAR, which Fabio will explain more later. It's on top of the front wing. It spans 360 degrees. It shoots 16 layers of laser and then calculate the distance. And plus minus 15 degrees vertically. And we put the camera, stereo visual inertia sensor, on top of the main roll hoop. These are two sensors that are based on different technology. They are placed in different places, and our goal was to have them redundant. So if one breaks, we still have to work with the other one. In addition to where the cones are, you need to know what's your speed. So we also included some inertia navigation system, which is a mix between a GPS and an IMU. We also included a ground speed sensor that made our life, well, we thought it would make our life easier. We also countered with the wheel odometry in case we wanted some redundancy. One tip that we learned throughout the season, and that one of our supervisors told us, is if you have extra budget, it's always a good idea to put it in sensors. You can deal with software, with noisy sensors, with bad sensors, with biased sensors, but if you can solve the problem upstream, you solve a lot of problems throughout the whole season. Regarding the actuators, we have a steering actuator, an emergency brake system, and the electric motors. We did our calculations and we found out that without the weight of the driver, we could brake and block the wheels only with regeneration from the motors. So we left the mechanical brake only as emergency brake system. The steering actuator it's a stepper motor behind the steering wheel that connects to the steering shaft with a tooth belt. And the emergency brake system, it's a pneumatic system that is mechanically preloaded. So it's an air spring that by default will pull the brake pedal and will brake the car. In order to unbrake it, we have a hydraulic system that needs several valves in series to activate. Once you activate this, you can unbrake the brake pedal and the car could move. One of these valves is connected directly, hardwired to the safety system, and the other one is connected to the software system. So the car has to be The safety system has to be closed, and in addition, we have to command that we want to unbrake the car. If anything happens, if the low voltage goes away, high voltage, whatever, inertia switch, anything, the car would stop being unbraked, and passively it will just come to stop. The software concept goes from sensors to actuators. So the first thing, as I said before, we're going to explain all this in more detail later, but we need to perceive the cone. So we have the camera pipeline and the LiDAR pipeline on the bottom. And they are independent from each other, so there's no allowed interaction, because if one fails, the other one would fail if they interact. So this cone estimates locally with respect to the car, and the velocity get together to a SLAM algorithm. SLAM means simultaneous localization and mapping. So you have to find out at the same time how does the map look like, and where are you in that map that you are building. Once we know this position in the map, we merge it with this acceleration from the accelerometers, angular rates from the gyros, position from the GPS, speed from the odometry and the ground speed sensor, and we get one state. One state meaning one pose and one velocity. So position and orientation in 2D, and velocity linear and angular. With this merged information, trajectory and control can decide which trajectory they want to follow and which control actions they want to apply to follow this trajectory. Basically, everything that I've explained is the high-level autonomous system. So what it's doing is replacing the driver. The result of all this has to be what a driver would do. So it would be a throttle command and a steering command. And we kept the old ECU untouched, or almost untouched. We implemented the low-level logic and safety there, because it's a real-time capable. But basically, instead of modifying everything that was already built in, we only substituted the thing that was removed. So the driver goes away, we just find a way to give steering and throttle. And then the ECU is the only one that communicates with the actuators and is able to send information.
So coming to the perception, where our goal is to detect those cones, defining the track boundaries. We have the two pipelines, as Miguel showed before. For once, we have the LiDAR, which, as shown, is there at the front, between the front wing and the nose. Basically, the pipeline works like this. We get the Velodyne data in, which is those 16 layers, as he explained, which rotate around. But whilst it rotates around, the car keeps moving forward. So we have to take segments and correct them for the speed and the yaw acceleration and the yaw velocity we have. Mostly yaw velocity, actually. So we take one scan, we put it into a world frame, we take the next scan, correct it with the current car speed and car angular or yaw velocity, put it again in the world frame and wait. We keep doing this until we have an entire revolution, so 360-degree scan. And then out of this 316-degree scan or revolution, we estimate where the ground is. So basically where the lowest points are, or there's different ways to do it. Just estimate where it is. As soon as we have this ground estimation, we remove all those points and just get points which are not ground. So that's cones, it's trees, it's people, whatever. In this case, basically here, it would be this table, this monitor, something like this. We take those points and we take those points of multiple revolutions, which basically stabilizes it. If we drive, the car is pitching a bit, and so it's a bit of a flickering. And if we accumulate points over multiple revolutions, that's a bit of a stabilization. And afterwards, we take those points. We're going to see a visualization afterwards if it's going a bit too fast. We're going to have all those non-grab points, in this case, like all those. This is a lot bigger than a cone. So we're going to cluster them. We're going to use Euclidean clustering, and we're going to see this cluster is way too big for a cone, so we're going to reject it. But this, on the other hand, could potentially be a cone. So that's what we are going to take into consideration and assume as a cone. What we got quite good at the results with it. What we discovered is that when we had high uncut grass on our testing fields, we got a lot of cone estimations on the side, which were wrong, and just to save computing time, we also applied a filter in there. At the end, we have a local cone map, which we can use for the trajectory generation later on. Let's see how it is visualized. So here you see the raw scan. Basically, there's all the revolutions which you have the scanner. To orient, it's kind of the top view, and we're basically driving on this track, which you see here. Then we estimated the ground, and removed those points and accumulated the non-ground points. Here you can already see quite well where the cones are on the track. And on the side, you see a lot of those noisy returns of the grass which was around there. Then, in the next step, you see the gray points were all the cone estimations at the beginning, and the orange points are the ones after the clustering. For the trajectory generation, they actually don't matter. That's why we have a safe radius here. So here you see a lot of points which should be filtered out, but we have a safe radius there because in hairpins, there could be potentially a lot of cones on the inside, and we didn't want to filter them out with the filter we have. So basically the filtering is just for computing time in our case. So there was one way to detect cones. The other pipeline is the visual pipeline. There we have the self-developed inertial stereo camera system, which you basically see here. Behind those two bluely illustrated lenses, there's a mono camera each, and also integrated in the 3D printed casing, there's a gyro sensor, as well as a USB hub to power it all and to connect it to the computer system. To detect the cones on the pictures, we have a machine learning cone detection algorithm, which basically differentiates between left and right cones and detects it out of the image. To put it all in three-dimensional frame, both of the images of both cameras are taken. There's features detected on both of the images, and they're triangulated and put into the 3D space which we have on the big screen. This is sped up. That's not. We were driving quite slow. It was one of the beginning videos to see if the algorithm works. And the frames are connected by integration of the gyro sensor. You see that there's a bit of a drift over the entire revolution, and at the point we're arriving soon, we're actually at the beginning of the track, but in the three-dimensional space, it looks like we're quite far off. But the ORP SLAM, which is basically the SLAM which we use for the visual pipeline, realizes that those features were at the same place before, or basically we've seen the same place before. It has to be the beginning. And that's when it basically corrects, closes the map, and corrects everything in retrospect. Out of the machine learning cone detection algorithm we have, like we can take those individual points, basically on the upper left you see, on the cones there's a lot of patches or parts which are very easy, or which are easily remarkable, and those parts are taken, and then basically out of those points you're going to see which ones are cones, and those are getting returned to the next step, which Miguel is going to present.
After the perception pipeline, we have the estimation, and basically estimation it's taking from the raw sensors or pre-processed sensor data, how do we merge everything into one single state that trajectory and control can use. So the first thing we do is a SLAM, as we said before, simultaneous localization and mapping. There are a lot of techniques for SLAM. One of them is the most popular, is graph SLAM, but for application we thought particle filter-based SLAM fitted best. Particle filter is based on having a lot of particles, and every particle basically is a different hypothesis of what your map could be. You add noise to them, and they start diverging and having different hypotheses, and then based on what you observe, so if you're observing cones, one of them will be more likely, and the other one would be less likely. So if I see these two things as cones, and one of my hypotheses is that I'm here, it's not that likely, because I'm seeing they don't match with what I'm seeing. So this is the general principle for particle filters, and this is actually what we use for SLAM. As observations for the cones, we can use either LiDAR or camera. And the data association problem, which is not trivial, is done through maximum likelihood. So which of the cones that I saw before is more likely to be the one that I'm seeing now again? And that's how we solve that problem. I'm going to show a video now. You will see all the different hypotheses in gray. When they go in straight, they start diverging. And then once they got into a turn, there's a characteristic geometry, and some of them get lower weight because they are not likely to be the true ones. So everything collapses. And then as soon as you see something that you saw at the beginning, most of them disappear except the true one. So the red one is the most, like the highest weight. The blue one is pure odometry. And the gray ones are all the hypotheses. And there, where you observe the other part of the track that we've been before, basically most of them disappear. Once we close the loop, we can extract the boundaries and know which cones are in the inside and in the outside. And then you can use the same algorithm to localize inside, just by freezing the map if you want, or you could even keep updating the map. One nice thing is that it doesn't need to know which cones are right or left. And this is good because if we lose the camera, we still have to be able to run all our algorithms. Once you get this position from a SLAM, so it's basically this top part of the diagram, it's too slow to feed it to a control algorithm straight. And also you may be noisy, so you want to smooth it out. You merge it with accelerometers, gyroscopes, and the velocities. And to do this, we use the Kalman filter. Kalman filter, you need to know the model of the sensor. So how does your sensor measure your state? And the model of the car. So how does the state evolve from one instant to the next one? Once you have this and you know how noisy each sensor is, you can apply this Kalman filter. If your models are nonlinear, then you would have to use a derived version, which is the extended Kalman filter, for instance. And this gives you one result. It merges all the sensors. One of the defects of this filter approach is that if there is any sensor fault or any outlier, it will pull the whole estimate to a wrong place, to a false thing. So we implemented an outlier rejection that it's statistically based. So if the belief before was that I was in position 3.5, and the next measurement for position is 20.47, it's very likely that I didn't jump, right? So you can do that just statistically, and we reject the ones that were 3 sigma away. Once you have this state, you know your pose and your velocity, you want to know where to go, right? The problem is that with the sensors that we see right now, we can only see reliably 8 meters ahead or something like this. So if you want to go at 50 kilometers an hour, like in the video we showed, in a straight, and there's a hairpin at the end, you have no chance of taking the curve right, braking on time, and doing the proper curve. So without the map, we decided to use one strategy, and with a map, we decided to use the other one. Again, it's a bit annoying, but our algorithms have to be color independent for the cones. If you knew the color of the cones, it would be a bit or much easier. But we don't know which ones are left and which ones are right. So this could be a nice way to go, maybe. Or maybe this is a nice way to go. So we build these trees that only try to avoid any kind of cone. And then we have a weighted const function that decides which one is more likely to be the good one. And that works quite nicely. It's not perfect, but it is useful enough to do the first lap while going slow. Also, it can take information from color if you have it, or it can even take information from the GPS if you know what is going to happen or how the track looks like. Once you do this, or you close the loop, you get the boundaries, you get everything. We do one optimization to get the best trajectory and which control actions you have to do to optimize this trajectory. We optimize for achieved distance, or like maximize the velocities along the middle line, projected on the middle line, and it's a fixed time horizon. So you can see that when it's going slow in the turns, the time that we use is shorter, or looks shorter, and then when we are going fast, it predicts longer in time, in space, not in time. Now you're going to see a video. The first part, it does this tree exploration, and then once it closes the loop, it jumps to the other method. To do all this computation and all these calculations of the algorithms that we just presented, we need some computing power. We needed a really rugged system that would not fail, and at the same time we needed a really powerful system that was able to handle, for instance, the vision algorithms, which take a lot of power. So we chose a master-slave architecture. The master is a really rugged computer, industrial grade. It doesn't need any cooling. It didn't fail throughout the whole season. And the slave is a really powerful computer. It overheats, or it heats up, it warms up, and it needs cooling. And anytime something needs cooling, it's not robust, because if the cooling fails, then the computer would fail. So we just prepared everything in a way that if the slave failed, we would still be able to run everything except the camera system. The only algorithms run on slave are the visual system. The housing is self-developed, it's suspended on one of the side pods, and we used no GPUs this year. We only based everything on CPUs. We already had those algorithms, or we knew that some may work, so we didn't adapt them. Now we're going a bit off topic and touching a lot of different things that we thought were useful or would be useful if you want to start a project or a driverless project next year. The tools are really important. It may seem like you are wasting time, but Without these things, you cannot develop a proper project, or at least that's our opinion. When you have 8 people coding full-time, there's a lot of packages and there's a lot of interaction between them. So we use the robot operating system, ROS, to link everything. It's just this middleware in between your operating system and the hardware, and between operating system and the software, so it's in the middle, and it interfaces everything. In addition, it's open source, and many people provide frameworks and tools that you can use, and they are pretty useful. Also, when you have 8 people coding full time, and they have to merge all their code, if you try to manage that without a proper version control system, at some point you don't know what's running on the car, you don't know if it works, you don't know if just people overwrote other people's files. So we use Git for that. And we also used continuous integration, which also took some effort, but helped us save time when testing. Every time someone pushed something to Git, it would get compiled, and every night it would get compiled from the scratch. And what this makes is that if someone pushes something that doesn't work, so that it breaks the whole compilation, then that change would be rejected. At least we know that our code runs when we go to testing. We developed a data management website in the same place. We could access it from the test spot. We could also access it from home when we were back. And it collects all the description, all the comments that we have about that day. Also, which software version did we use that moment, and which log data was recorded. Also, there was a guy working on online visualization and debugging tools, which saved a lot of time because they would allow us to see what's going on online. So at the beginning, we started with a visualization, and we could speculate, but you'd never really know what's going on. When we were able to see online what's happening on the car, you can solve the problems much faster. This is another tip that another advisor gave us. You can only be as good as the tools you use. So if your tools are easy to use, but they are limited, maybe it's good to start, but at some point, you cannot progress that much. Now we're coming to safety. We are dealing with really, really powerful machines. And in electro, we already have to take a lot of safety measures. Like you should never stand on the outside of a curve, for instance. But for driverless, you should not stand on the outside, you should not stand on the inside, don't stand anywhere near that thing. You don't really know where it's going to go. It doesn't have any common sense at all. It's the most stupid driver that ever participated in FSG, probably. So there are 2 goals. People have to be safe. And there's another goal, that is that the car has to be safe. So for people, again, stand far away, if possible, behind something. And for the car, it's always leave enough space. And also, for instance, software-wise. If you are able to measure how good or how confident your software is on what it's telling you, you could use that, right? Because, for instance, in the estimation, if you know that the uncertainty is plus minus 10 meters, yeah, you could leave the vehicle improvised, but you may as well stop it because you don't know what it's doing. It doesn't know what it's doing. So if you are able to retrieve some status of every package, and then the vehicle drifted and is lost, you should just shut it down. And then go and check what's going on. It's not worth it to try and see if it does it correct. You know, let it go, and let's see what happens. Bear in mind that if you crash your car, whether the season is over or it's going to be several $1,000s. For safety, for humans, or for the car, for safety distance, we made a nice Excel that it's really simple. So basically, you only have to input the reaction time of the person that is handling the remote emergency system. From our calculations, it's optimistic to be half a second, because it has to see that the car is going wrong, and then press the button, and the signal has to arrive. So all that in half a second is a guy that is paying a lot of attention. So that's good. Then you put a rules-compliant EBS. So 8 meters per second squared deceleration, and in less than 0.2 seconds it has to start, and then you can just do the physics math. So it's really simple. So first example, we go at 50 kilometers an hour, like we went on the video. You have to have in front of you 21.7 meters. Like this stage is 17 meters. So as soon as you're going this fast, it gets really bad, because this reaction time going this fast, it just pushes really far. And if you are turning, we put 15 meters per second square, which is not that off from a car turning in a sharp turn. It would be almost 12 meters to the side. If you go 91 kilometers an hour, like we went at the end of acceleration in FSG, you would need 57 meters ahead of you to stop, and 19 meters laterally. to the side. I don't know how much I said the stage was. It was 17 meters. Okay, this you require 19 or almost 20 to stop it. If it twitches to the side and someone stops it at that time, it may go 20 meters to that side. You can also do the calculation backwards. So if you only have 3 meters, how fast can I go? The answer is 12 kilometers an hour. So this is really useful. It gives you like a nice scientific idea of how much can you, or how fast can you go. And for us it was useful because sometimes we went to some testing spots and we realized that we had 2 meters or 2.5 meters. And we just, okay, how fast can we go? We can not go faster than 2.5 meters per second, 10 kilometers an hour. We went slow, nothing happened. But you never know. Sometimes we were not that lucky. We had to break our own rule, especially when you go to the competition. You have to be there. You are basically working the whole year to get there. And we almost had a heart attack, and you can tell. So yeah, that was real, of course, and that was less than 1 meter away from the tires. That was training, like testing on FSG. We would have smashed the LiDAR, that is the first thing on the front of the car. So it's quite risky. It's up to you to decide, but yeah, things happen and the car just goes off the track more often than you may think. A Formula student, a driverless Formula student car. It's still a Formula student car. Last year in scrutineering, out of 15 teams, 4 passed before every dynamic event, and I think these are the numbers, correct me if I'm wrong, 6 passed before the track drive was over. Out of, like 6 out of 15. So maybe, or at least we saw from our side, we may have been underestimating the time that it takes to prepare the vehicle to pass FSG scrutineering. You have to put a lot of effort there. It's like building blocks one on top of the other, and if you don't have a good autonomous system, you won't win. But if you don't prepare the mechanical and the electrical part good enough, you won't even be able to try. So put resources, and at least this year we are putting a lot of resources, manpower and money to prepare the car, especially with this new rule that you have to fully comply with the current rules. Our vision a bit for this discipline is like, as fast as electric evolved, we hope that this season or next season, we can count the difference between the top 3 teams in milliseconds, more in seconds or more than in minutes. We think it's going to catch up quite fast, at least some of the teams, and we are really excited to be part of this and to be contributing. We are aware that it's a really tough challenge, but we encourage everyone to do it. Also, we think the engineering that we are developing here and the education that is being done around Formula Student Driverless, it's a lot of is very valuable for the whole community of driverless and autonomous systems. So from our side, we want to contribute a little bit. Next month, or in the coming month, we will be releasing some data set of all our main sensors, or some of our main sensors. We are putting it together, and this way, new teams that don't have any data could try their algorithms, even if their car is not ready. Because basically, developing a car and developing the algorithms take a lot of time, and you cannot start with the data until the car is ready. So you could, it's going to be a totally different setup, right? The sensor will be in a different place. There will be different sensors, but at least you can start trying some crazy ideas, and you can start developing or getting used to some data. We'll just publish it at some point, and then if someone wants to know it, it will be like in the coming month. Just tell us. Some of the lessons that we learned in FSG is that we prepared our car as best as possible to not have problems there, but this is kind of common with electric. It was not about not having problems. It was about being able to solve them. I will show now some examples. So we made a list of everything that could go wrong. We could screw track drive. Track walk. So we may not have the LiDAR data, but it's really hard that we don't get the GPS data. Or this could happen, or that could happen. Well, everything that we thought could go wrong went wrong, and some other things as well that we didn't even think about. And then at the end, you've seen the really cool videos that we recorded, but performance is worth nothing without robustness in Formula Student. It doesn't matter if you ever went at 100 kilometers an hour in a straight. If you are not able to perform it that day at that time, it doesn't matter. So you'll also focus on the robustness, and it's better to do it 9 times out of 10 going at 20 kilometers an hour than do it, 7 out of 10 going faster. Because if it fails, you don't have second chances. This was our nice idea for track walk. We would put all our sensors here. We would map the track. If it works, we already have the map. We can go fast from the beginning. If it doesn't, well, at least we have the GPS data that would help us a bit. Yeah, well, this was the reality. At some point it was smelling a bit like smoke, and we had some electronic problems inside our main computer box. So it was not only the trackball that was in risk, but that was the computer box of the car. So basically everything was there in that box, 10 people trying to solve it. It was quite frustrating. You could not fit that many hands in there. With that problem, we could not go to do proper trackbook. We could not record our data properly. And actually, Munich were the guys that gave us some help there, and that increased a lot our chances of finishing track drive. So thank you for that again. This is our ideal skid pad. So this was like expectations. Okay, so yeah, the last 10 skid pads we did worked out of the box, no problem, and we were quite confident. In our best times, we almost matched up the best driver. We had a name set, and this was FSG.
And the car is off. Yellow lights flashing.
This is very quick. This is very quick.
It's looking very smooth. Oh, he is collecting some cones. Oh, and he smashed right into the timing equipment.
Just in case you haven't seen it properly, we took another take.
Yellow lights flashing.
This is very quick. This is very quick.
Looking very smooth. Oh, he is collecting some cones.
So yeah, I mean, really good that we could take that video to show everyone that we did it once, but then at the end of the day, that's not what gives you any points. Then I go back to you.
So at the end, we want to go back again to the fun part. For us, I guess you saw it at some points in between. It was quite hard at times, especially when it was not working. But this video basically shows where we drove the first time between cones. And I think you hear the people running behind the car, how happy they were. Fuck yeah! So this is what we hope you are going to take with you doing this challenge. Have a lot of fun. Step above the problems you're going to have. And just enjoy it. It's a really cool experiment. We want to thank Schaeffler and MathWorks for inviting us here, FSG as well, and also thank all of our sponsors for making this project possible, and all of you. And if you now have any questions, then feel free to shoot them.
Yeah, thank you again for the presentation and the nice insights. Yeah, does someone has questions?
My question is, did you develop most of your algorithms yourself, or did you use like a lot of libraries or ROS packages?
You need to use ROS libraries. At some point, the goal is not to code everything yourself, you can be really proud of, but the code that is out there is tested, it's working sometimes, and not everything worked out of the box, of course, but libraries for sure you have to use them, and ROS packages, we didn't use anything fully. No, the drivers, we use them, so like how to interface the LiDAR and stuff like that, we didn't use any software fully, but we were based on some, and the libraries, for sure you need libraries, like that's not a question there.
Hello. After your first lab and after you recorded the map, how fast did you get the position update from the SLAM? So how fast could you localize in the recorded map?
So the SLAM itself is running at 5 Hertz, but the state estimation is running at 200 Hertz. The control algorithm that does the fast part actually runs at 20 hertz. Does that answer your question?
Did I understood correctly that you used two different slams?
Yes.
One for the camera and...
Yes and no. So at the beginning we had some plans, and then some way through we realized that maybe it was not the smartest idea ever. So we still use the OrbSlam, that it's an open source available library for vision, for doing SLAM in vision, to get the 3D landmarks of the cones in vision. Once we had that from the car, so you would know that it's from the car, the cone is 3 meters and 2 to the left, you would put that into the SLAM that we presented. So at the beginning we thought we would have 2 different SLAMs and then merging them, and then at the end we end up having one, but we use the other one to triangulate the 3D landmarks.
So more questions? Yeah, then thanks again, and see you next year.
Thank you.